Okay, that is how you interpret the arithmetic mean filter expression over here. And then of course this filter, okay, if you can see in the last line there, is work best for Gaussian, uniform or gamma noise. So in other words, the previous step is actually when you investigate what is actually the noise affected your image. Once you identify the type of noise, and then you are managed to model the noise. Once you know that that noise is belong to either Gaussian, uniform or gamma noise, then uh, one of the suitable filter that you can use as your restoration filter is arithmetic mean filter. Okay, so because this is one of the filter that good in tackling uh, the provided noise there, uh, uh, whether Gaussian, uniform or gamma noise. Okay, so next filter what we have here is, okay, this is just some discussion there, example on how the the image which is affected with Gaussian noise. And then of course this variant actually you can calculate when you model the noise. And then if you try this one, then applying the arithmetic mean filter or average filter, then it improve a lot in reducing the strength of that noise inside your image. Okay, so instead of arithmetic mean filter, we also a lot of family that a lot of filter family that belong to mean. Okay, the next brother of arithmetic mean filter is called geometric mean filter. So this is the expression. Okay, in order for you to understand this expression, actually it's a similar things to be, you know, to I already discussed on how to translate the S, the surface of your capital S X Y here. Then you can understand very quick there. So in order to translate this thing, I will like to show you in this whiteboard again. Okay, again this is, it should be the same thing. Okay, your SXY actually is referred to the window. The different here now, the geometric mean filter is the expression inside here. Okay, so the any components there is similar, so meaning that this one is still your S XY. Okay, but this one is belong to S22. Okay, I just put SXY to make it general, SXY. So for geometric filter, if you want to calculate, because of course uh, just leave the expression like this is very hard for you to know how actually you want to make it or calculate. Okay, like this one, for arithmetic mean filter, you already know that to find all the f hit point, you just sum up together any point inside this window or this red box here, and then divide by 9. So I'll go for geometrics. It's not a summation symbol like this one. This one is summation symbol, but this one is, you know, it's a multiplication symbol here. Okay, this one is a not a multiplication, it's a product symbol over here. So actually for geometric mean filter, what is meant by this equation is, in order for you to find your f, let's say for example in this case still we want to count 1 point which is our f hit to 2, then it will, in order for you to use this formula, is actually you are your A time your B time your C, and then you time your E until your key. Okay, and then you put it to the power of 1/9. Okay, 1/9. So that's how you compute the single point of f22 if you want to compute this geometric mean filter. So you can see that this one is still represent any pixel that under or inside this red box here. And then the difference is just this one is not summation, this one is a product. So that's why you have a plus b plus c and a plus b plus c until k over here, and then you must put it to the power of 1/9. This one represent this one. So that's how you compute that's how you compute geometric mean filter. So now let's go back to this slide to see what are the best thing or what a feature that can be provided by geometric mean filter. Okay, the filter achieves smoothing comparable to arithmetic, meaning that in terms of smoothing behavior, this one also represents some smoothing operation if you are applying the geometric mean filter, but tend to lose less image detail in the process, meaning that if you are applying this one, actually it will perform the smoothing operation, but the blurring effect for this one is quite low as compared to that one, because that one is, you know, that's why they call it average filter. When you average filter, or okay, another name for arithmetic mean filter is average filter, because when you averaging everything, you are get a center number. In a set of number, you only get a center number. Then if you collect all the center number, it will become very blur to represent that's why that is the effect of the blurring effects happens. But when you change the plus operation into multiplication, then actually you can tend to reduce that blurring effects. Okay, so another things I would like to highlight here, you can see that this one is known as arithmetics because of the plus operation. Okay, this one is known as a geometric because of the multiplication operation. Okay, that one is plus together a, b, c and d divided by 9. This one is multiplication a, b, c until 9 numbers there, 9 item. Then you need to put all the you once you get the result, you must put or you must bracket it with to the power of 1/9. Okay, that is for the case of your, if you are using the window size 3x3, when your m and n equal to 3. Okay, but this geometric mean filter also have some disadvantage. Okay, one of the disadvantage is that if you see over here, okay, this is the same image as this one. Okay, they are using the same image. This is the input of, or this one is the input. Okay, when you apply the geometric mean filter, then you can see there what is the difference there. You can see any point which is black here, okay, as at the input side, will become very obvious at the output side. Okay, meaning that if the dark pixels is very small, then it become very big. And if the input consists of dark region, it will become very obvious at the output side. So why is that happen? Is because of the multiplication have some disadvantage. If you remember, anything multiply with 0 will make everything become 0. So that's why if you go back to this expression, okay, if you go back to this expression, okay, if you imagine that imagine that 1 pixel that inside this box is a black dot. Let's assume B is black dot. So if B is black dot, then black dot is black dot is represent, or black pixel is represented by 0. So if this is 0, the rest is not 0, then all things here will become 0 because of the multiplication. Okay, so once everything becomes 0, then your f22 becomes 0. In other words, if one of the pixel equal to the 0 inside this window, this red window over here, if you translate that window, then that is the result. Okay, meaning that if you have a small region of black dot, it will become bigger because of this effect. You are producing more and more black dot, and if you are increasing the size of the black dot inside your image. Okay, so that is the disadvantage of the geometric mean filter. So that is explained in this slide. Okay, now let's go to another family of mean filter, which is called harmonic mean filter. Okay, this is the expression of harmonic mean filter. So how to translate this one? By translate it by seeing this example, the same example. And again, for this one, okay, to get your f22, again I will use the same example, f22. Then it will become, okay, again we assume our window size is 3 times 3. Then this one, m times n will become 9. So I put there 9. Okay, doesn't matter, you can change the window size, but this one I just assume that my window size is 3 times 3. You can select 5 times 5 or 7 times 7, is up to you. But for this case, we just assume that our window size is equal 3 times 3. And then this one, how to translate, it will become what? It will become something like this. 1, you just put a bracket there, which is better, 1 over a plus 1 over b plus 1 over c plus 1 over e, and then you will do that until 1 over k. Okay, so meaning that there's a 9 items there, because you have 9 items there inside my red box there. So this is how you translate this equation. This is what is meant by harmonics mean filter. Okay, so now let's go back to the slide to see what are the disadvantage and advantage about for this harmonics mean filter. Okay, it's work well. Okay, before I forget, this one, geometrics mean filter. Okay, okay, for geometric mean filter, the noise that it can tackle is similar to arithmetic mean filter. Okay, it's suitable to be used to tackle noise similar to arithmetic mean filter. Okay, but for harmonics mean filter, you can see that this filter is work well for sud noise but fail for paper noise. Okay, if your image is only affected with sud noise, then you can use this filter. Okay, but it failed for paper noise. So why it failed in paper noise? If you remember, let's go back to the whiteboard. Okay, this is this expression. Okay, suds and paper. So suds, okay, suds I just write here. Sud is okay, but paper fail. So why it's fail? Okay, sud is just what happened in such noise. Sud noise is if your image is affected with one white dot. Okay, that is how you represent a sud noise. Okay, if your image have a single pixel of white dot, then it's a sud noise. So for paper, you have a black dot. So what happen if you have a lot of black dot? Okay, again, if let's say for example, this one, your B is your paper noise. Okay, let's say your B is paper noise. So of course, when B is paper noise, then if this B is paper noise, then your B should be zero intensity. Okay, zero intensity value. So 1 over 0 will become what? The whole thing over here will become infinity. So infinity plus the rest of a statement, then this one will become infinity. So at the end, 9 over infinity will make it produce 0. So in other words, if any point over here inside this window is 0, then it's also produce 0 over here. So it's actually, that's why this filter fail in dealing with paper noise. Yes, paper noise. Okay, because paper noise, you consist of 0, then at the end you back that paper noise, so it's failed to tackle paper noise. But for suds, it's okay because that is 255, nothing happens there. Okay, it managed to deal with sud noise. Okay, and the last family of mean filter is known as Contra harmonic mean filter. So this is the expression. Okay, this one is one of the I believe the complex mean family filter. Okay, contra harmonic filter, because the expression is very complex there. So now let's discuss about this for this expression. Okay, you can see that it consists of Q, which is a filter order. Okay, you can put any numbers there. That number will represent the filter order, and then what you can see there means for sus and paper noise. Positive Q eliminate sus paper noise, while negative Q eliminate the sud noise. If Q equal to 0, filter is arithmetic mean. Okay, now let's discuss about these two lines. Okay, let's discuss about the third line first in the slide. Okay, if your Q is equal to Q equal to 0, so what happened to the equation if the Q equal to 0? So here we will have some okay, the equation, this one will become 2, become 1. Okay, the order filter become 1, this one will become 0. So what had happened here? So GST to the power of 0 doesn't matter. Okay, doesn't matter your GST is what numbers there, but anything to the power of 0 will become 1. Okay, remember that. So that's why this thing, okay, in other words, you will have there 1, because A to the power of 1, B to the power of 1, A to the power of 0, B to the power of 0, C to the power of 0, and E to the power of 0. So at the end, the one that the total up here will become 9. Okay, because you have 9 items, 1 plus 1 plus 1, so you have 9 items there. So what happened to the upper part of this equation? Okay, so anything here to the power of 1 will become that item. So in other words, if A to the power of 1 become A, B to the power of 1 will become B. So in other words, it will become A plus B plus C plus D, S plus E plus E, and then until your K. So in other words, it seems to be like 1 over 9 A plus B until your K. So that is proof that if Q equal to 0, this expression is actually similar to this one, which is your arithmetic mean filter. So meaning that if Q equal to 0, then the contra harmonic filter mean filter will become the arithmetic mean filter. Okay, so how about Q is equal to positive? Okay, let's try Q equal to negative, because if the Q equal to negative, then it become harmonic mean filter. So what happen if your Q equal to negative? So if your Q equal to negative, okay, I use the red pen there. Okay, when your Q equal to negative 1, okay, assume that negative 1, so this one will become 0. Okay, this one will become 0, and this one will become negative 1. Okay, so anything here to the power of 0, it become 1. So A to the power of 0 become 1, plus B to the power of 0 become 1, plus C to the power of 0 become 1. So in other words, if you change it, if you try to arrange back the expressions there, it's actually the total, because you have 9 items A, B, C until K, then the total up will become 9. That is for the upper side. How about the bottom part? How about the bottom part over here? So it's negative 1. So negative 1, so A to the power of negative 1 plus B to the power of negative 1 until K to the power of negative 1. So A to the power of negative 1, okay, A to the power of negative 1 is actually equal to 1 over A. Okay, so in other words, this one become 1 over A plus 1 over B plus 1 over C until 1 over K. Okay, so this expression, actually if you go back to our harmonic mean, which is this one, okay, this is harmonic mean. So this statement is similar to this statement. So in other words, that's proof. If you set a q equal to -1, then it will become the harmonic mean. So the second statement in the slide, which is this one, you can explore by yourself. Okay, this one is very means. Okay, it's very good in handling the suds and paper noise. However, if you set the q the q in for positive number, it will eliminate the paper noise, while if you set the q negative number, it eliminate the sud noise. Okay, this one also can be proved. When you set the q equal to -1, it look like harmonic mean. So if you go back to the slide of harmonic mean and what we have discussed before as in harmonic mean filter, okay, it's good at dealing with such paper. So that's why that statement is seem to be tally with this statement, because if you put the negative q okay, the q is equal to negative number, it actually can eliminate the sud paper as sud noise. Okay, but of course it will fail to handle the paper noise. If you want to handle the paper noise, then you need to put the q equal to positive number. Okay, that is n for the mean family filter. Okay, so actually all mean filter here is related to kernel based neighborhood processing that we learned in image enhancement. And now let's go to next filter family, which is called order statistic filter, and this is actually also related to non-kernel based neighborhood processing that you learned before. So I will not discuss this one in detail. I think you're familiar with median filter. Again, this expression is actually represent in same as this version. Okay, it's try to provide the very standard expression where you each and every filter over here consists of, you know, this kind of expression. It consists of, you know, the surface of your capital S X Y. Okay, but the way how it perform or compute is similar. Okay, for median filter, like you have learned before, you need to sort all set of number under the window into all the pixel inside or overlap with your window. You need to sort into ascending order, and then you choose the center number. That is how you perform the median filter. And then for maximum and minimum filter also, mean filter also, you do the same. You sort it into ascending order. And for maximum filter, you choose the highest number. For minimum filter, you are choosing the minimum number, the minimum number. So the one that something new to you is what we call as a midpoint filter. Okay, so midpoint filter just not so difficult. Okay, it's just, you know, you just take the maximum value, which is come from this one. Okay, the same things here, maximum value, and then you take the minimum value, you plus together that minimum value and maximum value and minimum value, and you divide by 2. Okay, you do that pixel by pixel, and okay, you process it from, you know, from top left into the bottom corner, bottom right. Then you process the whole pixel. You process to the entire image with that kind of mechanism if you want to apply the midpoint filter. So of course this one also we have discussed before. Median filter is for, you know, median filter can be applied iteratively, but the image, okay, median filter is good in suds and paper noise, and then max filter is good in reducing the paper noise. Okay, max filter. And then mean filter is good in reducing the sud noise. Okay, this one have been discussed in the previous chapter. And this one, I just want to highlight this one, the new things that there's something that's new to you, which is Minpoint Filter. So for Minpoint Filter, so why we compute in this way? Okay, because this filter, okay, Minpoint Filter, okay, you just take the middle point between maximum and minimum intensity in large area of SXY. And this filter is good at reducing randomly distributed noise like Gaussian and uniform. And you find out uniform if you find out the Gaussian is very common, because Gaussian noise, if you identify, if you realize here, Gaussian, if you find out that your image is affected with Gaussian noise, there's a many filter you can use. One of it is Midpoint Filter, and then you can use many family of mean filter over here. You can use geometric mean filter, you can use arithmetic mean filter. Okay, Gaussian you can tackle many Gaussian can be tackled by many filter, but for um, midpoint filter, the one that special for to apply midpoint filter is this one, a uniform noise. Okay, if you find out that your image is affected with uniform noise, then this is the one that's very suitable to be used to tackle that kind of noise.